If you walk into a data center or server room, you'll find a lot of equipment there that runs using optical fiber. Instead of using copper with electrical signals to transmit information from point A to point B, we send light through a fiber to transmit that same information. This means we don't have to worry about the interference that you might get from other equipment or other radio frequency devices. This does make it a bit more difficult to monitor or put a tap into the connection. You do need specialized equipment if you're planning to use a fiber optic network. But unlike copper signals, which tend to degrade over a short period, in some cases you can extend fiber optics many kilometers without needing to regenerate that signal. And if you're working in an environment with a lot of industrial equipment or you're having to deal with a lot of interference, you could install fiber optic connections and not worry about any of those radio frequency interference sources. One challenge with fiber optics is that there are many different types of fiber and many different types of connectors. And in this course, we'll look at the differences between all of these and help you understand where the right fiber is used in the right situation. Here's a nice cross-section of a fiber optic cable. You can see on one side we are sending a light through the fiber. In this case, the light is being generated with an LED. In some cases, we use a laser to be able to transmit that light. This moves through the fiber optics on the core of that fiber. We refer to this as a high reflective index core, and it is surrounded with a low reflective index cladding to help protect it. Because of the differences in the reflective index, the light bounces back and forth through the fiber until it reaches the other side. This fiber, though, is very thin and very fragile, so to help protect the core and the clouding, we surround it all with a buffer coating. Here's an image of the end of a fiber optic connector. You can see the square-shaped connector along the outside. In the center is this white-colored ferrule. This is a ceramic ferrule that helps protect the fiber, which is on the very inside of that ferrule. If you look very closely, you'll see a discoloration. That discoloration is the fiber optic that's in the inside that is well protected because it's coated inside of that ferrule. That black dot on the screen represents where the fiber is inside of that ferrule. I'll remove the black dot, and now we can see the discoloration. That's your fiber optic cable inside of that connector. You'll generally run into two different types of fiber optic cables. One of them is a multi-mode fiber. This is commonly used inside of a building or any type of short-range communication. The distance on multi-mode fiber tends to vary, but it can usually go to about 2 kilometers in length. Because of the short distances that it needs to go, we can use a relatively inexpensive light source, and that's why we commonly will see LED used as the light source on a multi-mode fiber. We refer to this as multi-mode fiber because the fiber itself is relatively large. It has different modes that the light can take as it moves through the fiber. Each time the light is going through, it may use a different path to get from one side of the fiber to the other. This is very different than single-mode fiber. Single-mode fiber is designed for long-range communication, and some Ethernet standards can go kilometers through single-mode fiber without any need to regenerate that signal. Because it is going such an extended distance, we often will use lasers to be able to make sure that the light can make it all the way through that fiber connection. And unlike multi-node fiber, this single-mode fiber goes through the fiber in a single mode. You will notice that the core of the fiber is much narrower than the multi-node fiber. This is very common when working with single-mode fiber because you have a single path through the entire single-mode connection. Hope you now understand better.